The last portion of this section deals with approximation with derivatives. The idea behind this is that we know our derivative gives a measurement of the instantaneous rate of change. Our derivative tells us how fast the function is changing. Let's interpret how we could utilize this fact. If you are currently traveling at a rate of 5 feet per second, in the next 2 seconds, how far would you think you'd travel? Well, if you continued at a rate of 5 feet per second, in 2 seconds, you'd travel 10 feet. So if the instantaneous rate of change is 5 feet per second, then we could approximate that you would travel 10 feet in the next 2 seconds. Now, if you slowed down or sped up just slightly from that 5 feet per second rate, obviously you wouldn't get an exact value of where you land, but it is a pretty good approximation. If a human being is jogging along at 5 feet per second, in the next 2 seconds, how far would they have traveled? Well, a good approximation is 10 feet. And that's what we're going to be dealing with these derivatives. In example 5, we assume we know that plugging in the value 5 into our function h gives us a 10. And assume we know that the instantaneous rate of change at x equals 5 is 2. So we're at an x value of 5, and we know the derivative is at 5 is 2. That means we're changing at a rate of 2 units in y over every single unit in x. So let's approximate the following the best we know how. We are going to approximate h of 5.1, h of 5.01, and h of 4.85. Before I do this algebraically, I want us to think through how this is going to look graphically. So we know that our function passes through the point 512. When you input a 5, you get an output of 12. And we know that the derivative has slope 2. So the tangent line at that point is going to look like this. Now, that doesn't mean the function looks exactly like that. The function could look lots of different ways, but the tangent line looks like that. So what we could do is we can zoom in here to the point 512, and we could approximate where our function is going to be by utilizing this tangent line. So I've created a little bit of a slider here where this is my point sliding along the tangent line. So if we're at the point 512 and I know my graph is going in this direction, then what I can do is I can approximate the point 5.1, what value I'm going to get out, by just saying, where would my point be along this tangent line? How far would it have to move up? If I want to move below the tangent, to the left on the tangent line, I can just slide on the tangent line a little bit down. So we're sliding up or down the tangent line, depending on what my value of x is going to be. And even though I don't know what the actual function is, I can approximate using this idea of sliding along the tangent line. So let's do that algebraically. We already know you input a 5 into the function, you get out a 12. You input a 5 into the derivative, you get out a 2. So we approximate 5.1. So what we would do is we would say, well, the y value starts out at 12, and we want to add a little bit of our slope. Now, how much of the slope? Well, we want to add 0.1 multiplied times the slope, because ultimately 5.1 is the exact same thing as taking 5 plus 0.1. And so what you're going to do is you're going to just take the h of 5, which is the 12, and then add on 0.1 units, and we know the rate of change is 2. So we're going to take the y value, h of 5, and then we're going to add on 0.1 units, but the rate of change there is 2. So 0.1 times 2. And so a good approximation at an x value of 5.1 would be 12.2. Now we can do this for any value. So 5.01, we can say, well, we're going to start at h of 5 and add on a 0.01 multiplied times the derivative of h at 5. So we're taking 12 plus 0.01 multiplied times 2. So we get an approximation of 12.02 for my function's value when x is 5.01. Now, how about going underneath? Well, we're going to do the same thing. We're going to take my function value at 5, but instead of thinking of this as adding a number, we are subtracting 0.15. And so we're subtract 0.15 times the value of the derivative. So 0.15 times the slope of that line. And so it's 12 minus 0.15 times 2. Once I typed that in my calculator, I got an 11.7. So that's one way of approximating function values if I don't actually know the function. So if I know the tangent line and I know the point, then I can get pretty good approximations of the function by using that. I've said we get pretty good approximations of the derivative. Let's go ahead and calculate how good of approximation we could get. We're going to utilize f of x equals x squared plus 3x minus 2. We want to utilize that because we already know the derivative of that function. We've seen it a few times now. So the derivative of that function is 2x plus 3. Let's say we want to use x equals 4 to approximate the derivative when the x value is 4.1. So we want to use f of x, use x equals 4, and then approximate f of 4.1. So let's check this out. If we want to approximate, first off, we need what is the function give me out when I plug in 4. So 4 squared plus 3 times 4 minus 2. I got a 26. And then the derivative at 4 would be 2 times 4 plus 3, which is 11. So the function goes through the point 426 and has derivative at 4 of 11. So let's say we want to approximate f of 4.1. So just as we did last time, let's think of this as taking 4, take f of 4, plus 0.1 times the derivative of f at 4. So f of 4.1 is approximately equal to 26 plus 0.1 times 11. So 26 plus 0.1 times 11 gives me a 27.1. Now let's compare that to what the actual value is when you plug in 4.1 into the function. So just take 4.1 and plug into the function. That's 4.1 squared plus 3 times 4.1 minus 2. I can type that into my calculator, and what I ended up with was that the function value, when I plug in 4.1, is 27.11. Therefore, I got a pretty darn close approximation. We're 1/100th off. Now, what if we're a little bit closer to 4? Let's say we wanted to do this with 4.01. So all of this is still the same, except we just changed the 0.1 to a 0.01. You don't have to write that down. Whoops. So 26 plus 0.01 times 11, 26.11. And then if we typed in 4.01 into our function, we would end up with a y value of 26.1101. So notice that these are closer. When our x values were a 10th off, our approximation was 100th off. Now, since our x values are only 100th off, our approximation is a 10,000th off. So our approximation got better the closer my point got to the x value that I was using to approximate it. This is a really nice scenario that we can approximate without actually knowing what the function is or what the derivative is. As long as we know where it sits now, what position it sits now, and the rate of change it's moving at, then we can give a pretty close approximation, especially at values really, really close to the x value that we use. So in this case, when we're really, really close to 4, we got really, really good approximations. I want you to do the following problem. Try this on your own, and in the next video, I will solve them.